Welcome to The Explainer. Today we're going to talk about something you see literally everywhere, the simple but super powerful math behind anything that spins, turns, or whirls. We're talking about geometric rotations. If you just stop and look around, our world is just filled with amazing patterns. I mean, think about the swirl of a galaxy, or even something simple like the design on a hubcap. And today we're going to dive into one of the key mathematical tools we use to understand all of that, the rotation.
All right, so let's get right into it. What is a rotation when we really break it down?
So, what are we really talking about here? In the simplest terms, a rotation is just a turn. Yeah, that's it, a turn. Like, picture a spinning wheel, right? Everything on that wheel is rotating around that one single point in the middle, the part that doesn't move an inch. And it turns out, every single rotation, no matter how complicated it looks, boils down to just two key ingredients. First, you've got to have an anchor point, something that stays put. We call that the center of rotation. And second, you need to know how far to turn it. That's your angle of rotation. Every single point on the shape moves along a circular path by that exact same angle. Okay, so we've got the basic idea. Now let's see how this gets turned into a precise set of rules we can use on a coordinate plane. This is where it starts to get really powerful. When we're working on a graph, just kind of eyeballing a turn isn't gonna cut it. We need a toolkit that gives us perfect precision. And that's exactly what coordinate rules are for. They're like the step-by-step instructions that tell us exactly where every single point is going to land after a turn. Okay, this table right here, this is basically your cheat sheet. It's got the rules for the most common rotations, and they all happen around the origin. That center point, 0, 0 on the graph. So, for example, if you want to turn something 90 degrees counterclockwise, you just take your point, A, B, you swap them, and then you make that new first number negative. See? It's a super simple recipe you can follow every single time to get it perfect. And here, you can see exactly what that looks like on the graph. Just watch as that point, AB, takes a little journey around the origin. With each turn, boom, it lands in a new spot with brand new coordinates, all while following the rules from our cheat sheet perfectly. So now that we've got the rules down, let's actually put them to work. It's one thing to see the rules, it's another to see how it all comes together in a real example. You can really break down any rotation into these three simple steps. First, you grab the right rule from your cheat sheet. Second, you just apply that rule to every single corner of your shape. We call those vertices. And third, you connect the new dots, and there it is, your rotated figure. And here we go, you can see that rule in action. So the point R started out at 3, 1. We use our 270-degree rule, where A, B becomes B, negative A. So our new point, which we call R prime, lands right at 1, negative 3. You just do that for every corner, and the whole blue figure just swings right around to its new spot in red. Pretty cool, right? Okay, but what happens when we start mixing and matching? Well, things get even more interesting. You can combine different moves, and we call that a composition. It's like a 1-2 punch of geometry. You can rotate something and then reflect it, or maybe slide it and then rotate it. And this is so important. You gotta remember this. The order you do things in really matters. It's just like driving directions, right? If I tell you to turn left and then turn right, you'll end up in a totally different spot than if you turned right, then left. It's the exact same idea here. Swapping the sequence changes the final outcome completely. This example shows that perfectly. We're going to take that blue line segment and first we reflect it, like looking in a mirror, over to the red position. Then we take that red line and rotate it into its final spot in green. 2 different moves, 1 final result. This whole process of turning shapes around might seem a bit mechanical, but it actually leads us to a really beautiful and powerful idea that you see in both math and art: symmetry. So what in the world is rotational symmetry? Well, it's actually super simple. It's just when a shape looks exactly the same, even after you've only turned it part of the way around. If you can spin it less than a full 360 degrees and it lands perfectly on its own outline, it's got rotational symmetry. Take a look at this shape. If you give it a 90-degree turn, that's just a quarter turn, it fits perfectly back into its original footprint. It happens again at 180 degrees. But if you only turn it 45 degrees, see how it doesn't line up? That means 45 degrees is not an angle of rotational symmetry for this guy.
All right, time for a little pop quiz. Let's test this idea out on a few shapes you see all the time, because this is a special property that some shapes have and others just don't.
So let's check these out. First up, the parallelogram. Does it have rotational symmetry? Yep. If you spin it 180 degrees, just a half turn, right around its center, it lands perfectly back on itself. Okay, what about the others?
Well, this regular octagon is even more symmetrical, because all its sides and angles are identical. It maps back onto itself after a tiny turn of just 45 degrees. And then it does it again at 90, 135, and 180 degrees.
And last but not least, the trapezoid. This shape, it has no rotational symmetry at all. Go ahead, try turning it any amount less than a full circle. It's never going to land perfectly back on its original outline. It's a great reminder that this special property isn't something that all shapes have.
So, what's the big takeaway from all this? Well, once you get the hang of these rules of rotation, it's like you've unlocked a secret code. You start seeing this hidden mathematical order everywhere. Seriously, it's in flowers, company logos, snowflakes, even Ferris wheels. So the real question isn't if you'll see it, it's where are you going to spot it next?